is the story of the 80 days that preceded the launching of the IGY satellite 1958 Alpha. Designated Explorer, the free world's first Earth satellite, was designed and placed in orbit through the efforts of the United States Army Ballistic Missile Agency and the Jet Propulsion Laboratory, California Institute of Technology.
The Secretary of Defense announced this morning that the Army is to participate in the International Geophysical Year satellite program. The Army proposes to use the Jupiter-C missile to place a satellite in orbit around the Earth. The Jupiter-C will consist of a liquid propellant using the Redstone propulsion system. The Army is requesting the Jet Propulsion Laboratory to provide the following programs. First, the additional high-speed propulsion systems required. Second, the orbiting missile or satellite. And third, the necessary instrumentation to record and transmit the scientific data assigned to this experiment. Dr. Pickering, I think now we can...
Prior to the announcement by the Secretary of Defense, the feasibility of an Army-launched satellite had been investigated by Major General Medeiros, Commanding General of the Army Ballistic Missile Agency, and Dr. Werner von Braun, Director of ABMA Development Operations. In consultation with Jet Propulsion Laboratory scientists, it had been determined that the Jupiter-C missile was capable of placing a substantial payload in orbit around the Earth. Following the announcement by the Secretary of Defense, numerous planning conferences were held in Washington, D.C., Huntsville, Alabama, and Pasadena, California. On X-75 days, Dr. W.H. Pickering, Director of the Jet Propulsion Laboratory, made a short announcement.
The scientific experiments will be selected from those originally planned as a part of the U.S. IGY satellite program. The Jet Propulsion Laboratory has been assigned the responsibility by the U.S. National Committee of the IGY and by the Army to complete the design and construction of these experiments in a suitable form for the Army rocket.
As early as September 1956, the Army, in cooperation with JPL, had successfully flight tested the first Jupiter-C. The point of impact was more than 3,000 miles from the launching site at a predetermined spot off the coast of Africa. The purpose of the first test was to check the propulsion systems of the various stages, the problems of separation and ignition, and to demonstrate a new radio receiving technique called microlock. In subsequent tests, the Jupiter-C successfully accomplished the task for which it had been developed: to test the effects of aerodynamic heating on a nose cone designed for the Army's Jupiter Intermediate Range ballistic missile.
The high-speed assembly will be made up of clusters of solid propellant motors, like those that were developed for the earlier Jupiter-C missiles. A single rocket, to which we will add a cylindrical section to contain the instrumentation and a nose cone. This will be the final stage. It will be placed into an orbit and become our satellite. When the high-speed stages are fully assembled, they'll look something like this model.
At the Army Ballistic Missile Agency, teams of scientists and military personnel began the task of making final design changes required in the first stage rocket. These changes involved use of different fuels, a different guidance and control system and design, and the testing of a rotational launcher for the JPL upper stages. The Army called on Rocket 9 for the liquid propellant motor, which is a modified Redstone motor, and on Chrysler and the Ford Instrument Company for other components. At the Army Ballistic Missile Agency, full-scale static motor tests were conducted. At the Jet Propulsion Laboratory, the housing for the payload was being fabricated. Meanwhile, the Cooper Development Corporation and JPL were fabricating and loading the rocket motors at the high-speed assembly. The metal cylinder was constructed to contain two transmitters, their battery power supplies, and all the instrumentation needed to obtain and transmit data on cosmic rays, meteorite erosion, and temperature measurements of both the interior of the payload and its outer surface. In a machine shop at JPL, the finishing touches were applied to the rocket motor case of the satellite itself. The structure that supports the last stage rocket was also precisely machined. Then the rocket motor case and its supporting structure were assembled and checked for alignment to ensure the successful launching of the last stage. The voice of 1958 Alpha is this tiny transmitter, or more correctly, both of these transmitters.
This is the high-power transmitter that radiates 60 milliwatts of power and will operate for about 2 weeks. It will tell us the temperature of the outer surface of the payload and its own operating temperature. It will also relay information from an impact microphone that measures the frequency of collisions with small meteorites. In addition, it will transmit cosmic ray measurements. Both transmitters operate continuously throughout the orbit, and each will carry 4 simultaneous channels of telemetering. The expected lifespan of this unit is about 2 months, so when our high-power transmitter's batteries are exhausted, this low-power unit will continue to operate for another 6 weeks. Amateur radio operators will be able to pick up the signals from the high-power unit, but transmissions from the low-power transmitter, which radiates only about 10 milliwatts, can only be received by very sensitive equipment such as Minitrack or Microlock.
The radio receiving equipment for satellite tracking and telemetering is housed in enclosures light enough to be transported by helicopter. Some of the special equipment in these enclosures was built by the Radiophone Corporation of Monrovia, California. These and similar stations located around the world were designed to receive radio signals from both satellite transmitters. This receiver system was created specifically to function with extremely low power transmitters. The cosmic ray experiment, which was first proposed and developed by Dr. James A. Van Allen of the State University of Iowa, was combined with the transmitters in making up the payload.
This assembly, which is the actual payload for the satellite, contains both transmitters, the necessary circuits for the impact microphone, which will detect the collisions with meteorite particles, and a Geiger counter to measure cosmic ray intensity. The measurement of cosmic ray intensity outside the Earth's atmosphere should assist us in determining what cosmic rays are and where they come from. The study of the motion of cosmic rays will also tell us more about the Earth's magnetic field. The Geiger counter package with its associated circuitry looks like this. This tube is basically no different than the kind of Geiger counter you might use to locate radioactive ore. The cosmic ray experiment was originated and designed at the State University of Iowa, and the micrometeorite experiment was developed by the Air Force Cambridge Research Center.
The assembled Explorer satellite appears small, yet its single motor develops as much power as 5 diesel locomotives. 7.5 minutes from the time of the Jupiter-C liftoff, this satellite travels through space at a little over 18,000 miles per hour. The 2 transmitters we viewed earlier are contained in the striped cylindrical section just aft of the nose cone. The amount and thickness of the ceramic striping is calculated to control the average temperature of the instruments within this compartment. 4 flexible wires comprise the antenna used by the high-power transmitter. In flight, the satellite spins at more than 700 revolutions per minute in order to maintain directional stability. The wires are then extended by centrifugal force, acting on a small steel ball at the end of each wire. The spinning requirement imposed some added restrictions on the design, assembly, and fabrication of each component in the entire high-speed assembly. Not only the transmitters and the instrumentation, but the rocket motors as well were tested for their ability to perform in this environment. Centrifugal force might affect the structure of the solid propellant and thus affect the performance of the motors, a critical factor in the carefully planned sequence of events so essential to the successful performance of a multi-stage satellite launcher. The tremendous acceleration and the high vibration levels within the Jupiter rocket dictated that each component be ruggedly built and carefully tested. The transmitters were subjected to a simulated missile environment on a shake stand in the laboratory. The frequency and intensity of motion was based on conditions known to exist during flight. Signals from the transmitter were recorded and checked for any deviation or failure due to vibration. The weeks of painstaking testing, checkout, rework, and final assembly of the many intricate parts of the satellite instrumentation, the radio equipment, the rockets of the high-speed cluster, and their delicate ignition mechanisms was over. Now these units could be joined with the first stage rocket at the launching site for a final check of the complete system. At the Army Ballistic Missile Agency, the work of fabricating and checking the first stage rocket had been completed. The necessary modifications had been made to the launching vehicle, and the huge rocket began its journey from ABMA to the launching site. While the first stage was in transit, preparations were made at Cape Canaveral to receive components of the Jupiter C and start immediately the work of final assembly and testing. Scientists and equipment had already arrived, and the assembly of the high-speed stages was begun. With the installation of the payload and the final stage rocket, the high-speed assembly was a complete unit. The final balancing tests were made to ensure the successful operation of the components. During flight, this assembly is spinning faster than the wheels of a racing car. With the arrival of the first stage rocket from the Army Ballistic Missile Agency, the Jupiter C began to take form. In the assembly building, the balancing operation had been completed. The tub that contains the high-speed stages was given a dress coat of paint. Now the cluster was ready to be joined with the first stage rocket. On the 80th day, Explorer was ready for launching. But at X-10 hours, it was reluctantly decided that because of hurricane velocity winds at high altitudes, it would be inadvisable to fire. A 24-hour hold was called. On January 30th, it appeared that the weather might improve. The odds were not good, but the countdown was continued to X-2 hours. A second time, the order came from General Medeiros. Hold 24 hours for weather. Due to other range schedules, launching had to be accomplished on the following day, January 31st, or the firing would be delayed for a week. By noon, wind velocities had reduced to 160 miles per hour. there was evidence that the weather might continue to improve. Accordingly, final adjustments and checks were made of wiring circuits and instrumentation. The batteries that energized the igniters of the high-speed rockets were installed and checked. The transmitters were tested. During the final hours of daylight, the fuel that powers the first stage was pumped into the big rocket. In the past 6 hours, hundreds of detailed operations have been performed. The igniters that will fire the high-speed stages have been brought from the storage area and connected. About 10 minutes ago, it was decided that weather would definitely permit the firing, and the liquid oxygen loading was begun.
This is Project Command. At my command mark, the time will be X minus 75 minutes. Mark, X minus 75 minutes.
Men are moving out of platforms 1 and 2. In a few minutes, service platform 3 will be evacuated, and the gantry will be moved back from the launching pad. The propellant loading has been completed, but it will be necessary to top off liquid oxygen overflow, taking readings before and after topping.
Attention all personnel. Please clear the launching area for radio frequency interference tests. Please clear the launching area.
This is range.
Command transmitter on.
Telemeter on.
Frequency measures 2.5 low.
Calibrator on.
Dovap on.
Cape radar off. This is Project Command. The time is now X minus 33 minutes. Authorized personnel may resume work on pad. Resume work on pad. Hold for final transmission test. This is Project Command. At my command mark, the time will be X minus 15 minutes. Mark, X minus 15 minutes. All personnel clear the launching area. All personnel clear the launching area. The signal is 2.5 kc low. Channel 1 is now reset. Channel 2 is reset. Channel 3 is reset. The figure for Channel 1 is 430. Channel 4 is reset. Channel 5. This is Project Command. The time is now X minus 13 minutes. Start vibration records. Begin cluster run-up.
The cluster is starting its spin. Transmission of all payload electronics components is now being monitored.
This is Project Command. The time is now X minus 4 minutes.
After the firing signal is given, it will take almost 16 seconds for the vehicle to take off. Pressurization will be started at X plus 3 seconds. At X plus 14 seconds, ignition will begin. Thrust buildup will continue until liftoff at about X plus 16 seconds.
This is Project Command. At my command mark, the time will be X minus 1 minute. Mark, X minus 1 minute. Stand by to power transfer. Firing key to launch. Clear signal for firing. X minus 30 seconds. Close master safety circuit breaker.
Recording's on.
Time is X minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Pressurization start. X plus 8, 9, 10, 11, 12, 13.
That at 5 seconds past 10:55 p.m. on January 31st, 1958, Satellite Explorer was placed in orbit. This achievement is another step forward in man's drive to better understand the world and universe in which he lives. We are no longer earthbound. Soon we will begin to explore the solar system far beyond the boundaries of our tiny world. In the years to come, man will continue to use rocket vehicles like Jupiter C to expand the frontiers of knowledge.